Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a great pleasure to introduce Damon Wishick, who's visiting from University College London. Damon is a research a fellow of the Royal Society, is that right?
I have a research fellowship from the Royal Society.
Okay, a research fellowship from the Royal Society, and he's working on IP and Ethernet congestion control, modeling, networking, multipath routing, buffering in switches, P2P networks as well. And today he's going to give us an interesting talk about short messages.
Thanks. Thank you for the invitation to speak. I'm just going to start off with a few quick slides.
Tell folks when you'll be around to follow up.
I'll be around Tuesday through Friday of next week, and it'll be great to talk with people in those times. I'll start by saying a little bit about, first of all, introduce myself and the group, UCL Networks Group, and these are the 4 people in it. There's Mark Handley, who's been around Internet Protocol design for a long time, Kyle Jameson, who's just arrived from MIT, Brad Karp, who works in distributed systems, previously from Carnegie Mellon and Intel, and me, and I come from a maths background, and it's a bit of adventure seeing what computer scientists work like, think like. I'm going to talk about short messages, but I just wanted to have a few quick slides saying what other things I work on in case that triggers any interest. First question was queuing theory for TCP. The question which I've listed up here, how big should buffers be in core internet routers? It's a strange question. There are several different answers which differ by orders of magnitude. Cisco builds in roughly 4 gigabytes of memory, which may not sound like a lot, but it's terribly fast memory, so massively expensive, very hard to get right. There was an exciting paper several years ago by Nick McEwen from Stanford who said, no, hold on, that's crazy. You only need 40 megabytes. And actually, I think the answer is you only need 30 kilobytes in internet routers, no matter how big they are. This is clearly not an engineering question. This is a maths question to try and get right orders of magnitude scaling phenomena. And so the answer to this question, how big should routers be, you need to bring in queuing theory, and you need to understand stuff about synchronization and so on, a long-standing question. It's about TCP. So there's topic 1 I won't speak about.
Did this have impact? Did people start buying smaller memories? Or, I mean, what did this lead to?
I don't think the internet router people really have done anything. There's no point in them because Cisco and Juniper have worked out how to do very big memories. That acts as a very good barrier to entry for smaller companies to come in. So Cisco and Juniper are happy with the status quo. The companies who actually want to do stuff, they use like Ethernet switches, which just have small buffers in anyway. And BT's 21st Century Network, they've configured the buffers to be small because they've worked out that's what you need for good performance. So it's something that people are doing, but no one's really acknowledged it. I think that's the status. Topic 2 I won't be talking about is scheduling in switch networks. A switch network, I've got a picture of a roundabout here. A roundabout, there are 4 roads coming in, so 12 possible traffic flows. There may be customers from the south who want to go north, from the north who want to go east, and so on. And the scheduling problem is which cars get to flow through the system when. And so with David Rutschar from MIT, we've worked out the queuing theory behind this, and this leads to ideas about what the best way to schedule it should be. It's a very general model. We've applied it specifically to input queued switches in internet routers. It's the same sort of model to describe road roundabouts. It's the same sort of model to describe locks in databases. So it's an interesting thing which I hope will go further. Another piece of work, this is more internet architecture stuff than maths, is what we call the resource pooling principle. The idea of resource pooling is if you have a network with a whole bunch of things with capacities, you want them all to behave like a unified whole. You don't have to worry about, well, I have this much memory here, this much processing there, this much bandwidth here. You want them all to behave as though they're lumped together. In other words, you want to achieve resource pooling. Resource pooling is the only way to achieve a reliable network. Telephone networks have implemented it from I guess, the early 80s. It's the only way to achieve reliable service on cheap hardware. It's so useful that everyone has discovered it sort of independently, like AT&T and British Telecom have it in their phone networks. Enterprises have multi-homing of their sites. That's a form of resource pooling. Peer-to-peer networking is also trying to pull upload capacity. Even, I would argue, packet switching, the core architectural principle of the internet, is a type of resource pooling. You're trying to make better use of the bandwidth, trying to share all the capacity of a link. And everyone's built in different mechanisms, and they all clash horribly, especially the BGP traffic engineering type mechanisms. And we believe that multipath routing, if you give the end systems, the TCP systems, the ability to split their traffic over multiple routes, then it will get virtually all the benefits of resource pooling that everyone's looking for. That's the beginning of the research agenda. There aren't really any definite results here, but it's an exciting area. Okay, so I'm not going to talk about those three things, but if there's anyone who'd like to talk to me afterwards or ask questions, I'd love to.
I'm just wondering if the remark you made about TCP holds true for short messages.
Short messages would benefit from multipath, and I'll get to that later on. Okay, so now the actual talk, short messages. And there's a paper up on this on my website. This is an outline of the talk. I'll go around in a circle and end up roughly where I started. I'll start off talking about networked applications. The networked applications, basically what it seems to me, the way I use computers at any rate, is no one cares about how fast an individual computer is. All computers work lightning fast compared to what you actually do with them. What you actually do with them is you access things over a network. And it's accessing things over a network which is the real bottleneck. And that's the thing we need to get right to have good responsiveness for computer systems. So I'll talk about, first of all, some very simple sorts of network applications that we might think about. To understand what's going on there, we need to look at what type of network they're running over. So then I'll talk a bit about network theory, network modeling, traffic modeling. And based on these ideas, I'll then move on to distributed algorithms, which will be a more formal way of expressing these classes of problems. And then I'll go back and end up where I started and think a little bit about particular suggestions for networked applications. All right, so this is where I'm starting. Here's an example of the most canonical networked application, just a web browser. And what I'm doing here is I'm going to a particular website, Slashdot. This was motivated by frustration, basically, this talk. Sitting in it was a hotel room in Stanford where I reliably got round trip times of between 2.5 and 3.5 seconds. I couldn't work out what sort of networking stuff might be going on there, but it was really, really horrible performance. There's a comment here by Mark Handley. He's the guru of UCL networking. He said, in a perfect network, all transfers should complete in one round trip time. That's obviously the best you can ever hope to achieve. So let's see what actually happens when you go to Slashdot. Type in the URL, waiting, transferring data, that's a good sign, waiting for images, waiting. We've got something. Waiting for ads from Google. More waiting for ads from Google. Waiting for ads from DoubleClick. Waiting for, I guess this is some sort of tracking, eyeball tracking. Images. Next one's very important. I think it's giving us the rounded corners. Waiting for Google's web service tracking. And now we're finally done. So it's not one round trip time. it's stupid that web users have somehow become conditioned to live with 5-second delays, 10-second delays in just retrieving a web page. I don't understand why it is at all. I don't see why anyone should have to wait more than a few hundred milliseconds, but we do. We just put up with it. This is a really nice visualization. It's called Firebug. I'm sure several people here have tried it. It keeps track of all the different pieces that are loaded, and it tells you when the download started and how long it took. One thing which is interesting here is that the time it takes to download an item has virtually no relationship at all to the size, as 37 kilobytes took 1.83 seconds, 62 took 5.82 seconds, and 4 kilobytes under a second, 21 kilobytes in 300 milliseconds. Basically, there's no relationship at all between file size and how long it takes to download it. That's a slightly silly thing to say about networks, but it's just true. For the performance of these things, bandwidth is simply not an issue at all. Here's another example.
What is
The issue is, the latencies come in several ways. There's the latency of propagation delay, just how long it takes light to get there, serialization delays. There's delays due to message drops and timeouts, and then there's delays of the server at the far end. I'll be talking much more explicitly about some of the network-related drops. I won't be talking about the latencies caused at the back end. Here's another example I looked at. This is if I log on to Hotmail. From the instant I click on login on Hotmail, what has to happen? Well, first of all, it goes to retrieve this thing. This is a secure item. That tells it to retrieve this item, which tells it to retrieve this item, which tells it to retrieve this, which tells it to retrieve these, which tells it to ... and it goes down here. So just to get your inbox, there's an awful lot of backwards and forth, to and fro's. And what's more, some of these are structured in sequence. I mean, this thing tells you to retrieve this, which tells you to retrieve this. And so just the height of this tree gives you a bare minimum number of round-trip times before we get to see the inbox. One thing I found really, really bizarre here is I had always been taught that reliable delivery is something which TCP does. You know, TCP sends a packet, it waits for an acknowledgement. If it doesn't get the acknowledgement, it will resend the packet. And so you achieve reliable delivery through TCP. But that's not what this does. This has reliable delivery in JavaScript. So the JavaScript sits there and it sends an HTTP request. If the answer doesn't come back in time, it will send another HTTP request. And I marked out those items with a bold border. And I can't work out any rhyme or reason behind why some bits are reliably delivered and other bits aren't. Why is it that Windows Live wanted to protect this and this and this and this, but not some of the others? Anyway, I don't know what the answer is at all there, but at least it's telling us something. The fact that people are forced to get reliable delivery in JavaScript in the body of their web pages says, I think, that there's something wrong with the way we think about reliable delivery and the way it's layered in the stack. Here's another example. This is from Google. This is what their web page used to look like until December last year. They have a much longer, taller tree there. They switched it in December last year because they did a whole bunch of rewriting their code. And in particular, they rewrote their web stuff to make it load faster. And they ended up with a slightly flatter system here. Again, I really have no idea what the software engineering is behind the structure of this. I've only looked at the behavior of my web browser to try and track what they're doing. Okay, so let's look a little bit in more detail at some of these. Let's say to retrieve a single one of these items, what needs to happen? Sorry, before I go on to an example, I'll try and say something a bit more abstract. Abstract problem statement. A network transaction. These are all examples of what I will call a network transaction. I'm not trying to fit into any established literature here, but this is just a convenient word. A network transaction is the coordinated exchange of short messages between computers on an unreliable network. The example I've given here are reliably retrieving a web page. Other examples might be just reliably delivering a message along a path in a network, or electing a leader in an ad hoc network, or sharing state between players in an online game. So network transactions, that's basically what I mean by short messages, by the title of the talk. I didn't say what the file sizes were in those web page examples. They're all very short. None of those items, none of the 60 items which Gmail downloads are more than a few kilobytes big. So, right, now I'm going to drill down into some of them. To retrieve a single one of those items, there's a dialog which goes in. The client says hello. The server replies hello. Client says, OK, please send me the data. Server says, OK, here's the data, goodbye. And client says goodbye. This is what just, if you have HTTP running over TCP, this is the exchange of messages needed to retrieve a single one of those items. 9 packets in total, 2 round trip times until the client hears the answer. All right, so what does TCP do to behind the scenes to cope with the fact that the internet is unreliable? It does reliable delivery. Let's say the client here, it sends the hello message, and if it doesn't receive an answer back within a certain timeout period, it will resend the message. The trouble is that these retransmits can be very, very slow. The standard is that the retransmit timer is 3 seconds for the first packet in a sequence of messages. So if you think with that let's say Microsoft example, it's got 45 items to retrieve. Each item has 1, 2, 3, 4 messages which need to happen. So that's an awful lot of messages where there can be drops. If there's a drop, you can lose an awful lot of time from the user point of view. And the larger the web page, the more complicated it is, the more the problem. So this timeout rule, this is what TCP does for short messages. It has a different retransmit mechanism which kicks in when you have large things to transfer. Yeah?
What is RTO?
RTO, they call it retransmit timeout. That's what it stands for. So you just send it, you wait an RTO, and if you don't get it within a timeout period, you resend it. And each side in the communication uses its own RTO timer, and it updates it. It tries to get RTO equal to round trip time because that's a plausible thing for it to do. But for short messages, there's no time, so it just uses a very large timeout value to start off with. So basically, a timeout is a real killer, and in complicated web transfers, you're very likely to be killed. Yeah.
On your first packet, is that a data packet, or is that like the SYN-SYNAC ACK sequence?
That's the SYN-SYNAC.
Is there any kind of analysis of how prevalent timeouts are in a typical transfer?
Yes. Here's a paper from people in Cambridge Computer Lab, the effect of early packet loss on web page download times. So they look specifically at this question. It was a measurement study in the field, so they were looking at what it was back in 2003.
How did they do that? What were the clients?
They inserted a probe in the campus network, and the probe did, it looked at the IP packets, then it looked at TCP, then it reassembled the HTTP requests inside, and so it produced you stick a probe somewhere in the network and it produces a complete picture of what the web pages that the user was downloading were. It's a really nice visualization tool. So you can look at a problem and then drill down and see which particular packets caused the problem. That system was called nprobe or xprobe or starprobe, or I think it changed its name several times. Yeah.
So the packet losses in the initial SYN, were they primarily seen to sort of less popular web servers or major web servers?
Sorry, could you repeat the question?
So on a short web page, the SYN timer is probably what hurts you the most, right? I mean, obviously, any timer will hurt you, but the first SYN timer is going to hurt you the most. I'm just curious, if these people saw SYN timers in this paper, were they primarily to less popular web servers or major web servers, or
I don't know. I don't think it's a question of who the web servers are. It's really a question of what your network provider's like. And in the UK, at any rate, the serious problems would be at the link from the core to your local exchange. I think if you're a US cable subscriber, the problem will be the uplink from you to your base station. Or I think basically the problems will be caused by your network provider, not by the web server.
Yeah, it's usually the interstitial network where you have these losses. It's usually not either interlinked.
The only reason I was asking this is because I don't remember the exact paper, but there was, I think Louis Julius did this a while ago. He said that less popular web servers actually have poorer connections to the network. So it's not your link that causes the problem. It's the web server's link to the, some guy is running a small blog posted in some bad hosting provider somewhere in Podunk. That's what causes problems.
But you can imagine that, my wireless router, I have a noisy wireless environment, there's a whole bunch of stuff in a consumer network, so local that's not reliable, period.
For a long time in the UK, it was the transatlantic link to the US, which was the severe bottleneck. I think basically the hotspot moves around the internet, and there are cycles, and it's very hard to know precisely where it will be. Yeah.
So is there a difference between the rate of first SYN drops versus regular other than data packet drops?
I don't know the data. I'm sure there is, but don't know any data points.
The network would just be forwarding packets, so it will flow they do this on a route. I'm trying to figure out why it would drop the first SYN more so than it would drop any other packet.
It doesn't.
I wouldn't expect. So the question is, should it be the same packet drop probability for a SYN as for a data packet? I would guess it's possibly the same. Possibly the network has mechanisms to give priority to SYNs. I think that's unlikely.
The only reason I can think of, especially wireless links are a problem, is that SYN packets are smaller. So there is a very, very small probability that SYN packets will actually experience less loss than data packets.
Yeah.
But that's all minor details.
Yeah, I think that's very, very negligible.
Yeah, I just wanted to curious. I was trying to track out what you're saying. That's all. Thank you.
Any major conclusions from this paper? Do you have
No, I mean that it's a problem, that this is the serious component of poor quality of service for users, but that's all they concluded really. This is an example of a more complicated network transaction. This is a HTTPS thing where you say, hello, let's use the cipher. Okay, here's my public key. Okay, here's a secret key for the data. Okay, and now the client can send its request. So, like Google, the very first two things are secure items, and those have an awful lot of to and fro's. Here's another example. This is if you do a directory listing in Windows, as far as I can tell. I don't know if there's anyone here who can correct me. This is the way it works. You send a message saying, find the first file in a directory. It replies with the first file. Then you tell it, find next file, and it replies. And so to do a directory listing of a large directory, you're exposing yourself to all sorts of problems here. So why are they programmed like this? It seems to me that from a naive networking person point of view, that you might as well just send the request, and the thing should prepare the entire answer and send it to you in one great big chunk. Why doesn't it do that? I don't know. Here are some guesses. First guess, the programmers just want to get a working bug-free version out there quickly, and so they're not so concerned about network performance. Guess two, that these are examples of lovely, elegant modular code, and maybe it's split into development teams working on different features, and they split it up in this way because it's the most natural way to split up their web pages. My third guess, which I was disabused of last week, was that programmers, for example, here at Microsoft, have wonderfully fast campus systems where everything works perfectly. And so they're not aware of how bad it'll be when things don't start working. And then that's not actually the case. So these are my guesses. I really wouldn't need to work out why people... I'd need to talk to someone like this to find out why they're actually programming here.
On the network side, GNS, we've seen the last one fairly common where all of a sudden you get 120 milliseconds from Bay to Dublin, and it just blows up an application. It happens. Doesn't happen as often as the others.
Okay, so I've said a bit about the sorts of problems that I'm interested in looking at. And now I'm going to talk about, well, obviously the behavior of these things depends on the network. So now I'll say a bit about what we need to know about the network. Here's the most basic thing, mice and elephants. This by now is a very old story from early 1990s, mainly Walter Willinger from AT&T and groups of other researchers, they discovered this phenomenon. Most traffic on the internet is composed of large traffic flows, which are called elephants. Nowadays, think of an elephant as being a high-definition movie download. And yet most network tasks are made up of very short flows, which are called mice. Mice are tiny, like 1 packet big, 5 packets big, and they're very, very numerous. There are way more mice than elephants.
Sorry, how do you... I feel like that's in conflict. So most traffic, so volume-wise, it's mostly elephants?
Volume-wise, most bytes are from elephants. Most flows are from mice. Is, I guess, the definitive early measurement study by Crivella and others. There are various theories about why this happens. These people, John Doyle and Carlson, argued that mice and elephants arises because it's the optimal way to split up your data. If you have a user who's doing queries, first of all, they want a quick look at the table of contents, and that will enable them to make a quick decision. And then if that's not enough, then they'll go and look at something larger, which will enable them to make a further decision and go on to something else. So they had an argument about optimal partitioning of data, which said that's why there must be mice and elephants in a data network. But then they went on to say basically mice and elephants happen everywhere. They looked at forest fires in California and decided that if you look at the size of forest fires, there's a small number of forest fires which cause a huge amount of devastation, and large numbers of small fires which don't do very much. And same with earthquakes. Same with virtually everything in the natural world. It obeys these power law distributions. So whatever the precise cause of heavy tails, they're here, and we're just going to live with them. And I'd say more generally, any network at all, any general purpose network will always be designed to carry mice and elephants, because users just want to send elephants, and that's all networks carry elephants. And elephants are what network traffic engineers spend all their time looking at. This is a picture of a head of cauliflower, which shows a reference to self-similar characteristics of network traffic, which is what all this research from AT&T was. Important network traffic properties are governed by the large flows. Therefore, if you look at what network engineers, traffic people do, they only ever look at the elephants, which is a big mistake, or it's missing out a large part. Most traffic comes from elephants, and so capacity planning is based on elephants. But what users really care about is the mice, because that's what makes up the user experience, the interactive user experience, sitting there exchanging very many short flows, composing which go to compose a complex task. Here's a quick example. You're on your iPhone sending an SMS saying, "I'm trapped in an avalanche," and giving your coordinates, which is 50 bytes of text. Please wait, busy downloading, iTunes update, 1.7 megabytes remaining. Okay, so mice are really important to users, and somehow they've been a bit overlooked by the network traffic community. What does it mean for our purposes, for how to improve things on networks? Well, here's a really simple brain-dead answer. To speed up transactions, because of the problem of this early packet loss on the performance of web page downloads and so on, why not just send multiple copies? This is a very, very simple form of forward error correction. So instead of sending one SYN, you send 5 SYNs together. If you do this, it would not cause very much extra traffic at all. Here's something which I found really striking. I have 2 different schemes here for aggressive forward error correction. This one's the fairly simple scheme. I'll imagine a really simple hack to TCP. I'll make TCP send 3 copies of the first packet in each flow, 2 of the second, and 1 copy of the third packet in every flow, and 1 copy of every packet thereafter. And I asked, if you did this, if you enlarged each flow in this way, how much extra traffic would it cause? Answer, in 1984 it had increased traffic by 34%, and in 2005 it had increased traffic by 2.7%. So what's happening here is that the elephants are just getting bigger and bigger and bigger. Back then, I don't know what the elephants were. They're FTP downloads of programs, of short, small programs, I guess. Here, the FTPs, in 2005, I guess it's downloading short movie clips. Now it's downloading high-definition movies. Yeah?
That depends on what your assumptions about the loss process is. If you send multiple copies of the same packet, and the losses are very bursty, you're not going to do a whole lot better.
Yeah, I'll come on to that in a moment. And there's a comment here. There's no point sending packets too close, because if you send them too close, they'll share the same fate. So
if you want to provide RTO, the only thing that you need to do is keep the ACK clock going. So I would argue, and this is, I think, something that John Crowcroft had proposed earlier, is simply send smaller packets. Rather than sending bigger packets, send a large number of smaller packets.
But there's no point. This idea of keeping the ACK clock going, that's something suitable for when you have a large flow or stuff with many packets. The whole thing about short flows is that they're such a tiny fraction of network traffic volume that you might as well just send multiple copies at the same time.
But your problem there is you're going to saturate a network gear which works on packets. It doesn't work on the flow. So, in other words, when you program...
No, why? You won't saturate the network because... Here I'm just, how many more packets in the network am I causing? 2.7% more packets.
Messenger applications, which have very many tiny packets, they will melt a router in many cases just because of the processing needed for each packet. The routers and switches work on packets. They don't work on the data. You can care less about data. So the smaller a smaller network packet takes a lot of time. So you increase the amount of work the switches and routers do, you saturate the backplanes and the cores.
Yeah, this will definitely help you on the very short packets. Typically
anytime you increase the number of packets, you increase the load on the network applications, which load up buffers, network certain devices, which load the buffers up and so on, you cause drops and congestion.
But if all the packets are the same size, then it's traffic volume which matters rather than number of
packets. You increase the number of packets.
Okay, but what's the increase in number of packets? The increase in number of packets is negligible if you do this.
I think your point is that the increase in number of packets at a link in the middle of the network, in a backbone link, is going to be negligible.
Yeah.
But when you think of an application like Messenger, where you've got servers that are being pounded by millions of
yeah, okay. So that is definitely an exceptional
packets.
case. Or another example would be a DNS server, which only has mice. So I said any general purpose network has mice and elephants. The thing is, a DNS server is not really a general purpose network. It's a very specific thing. So this will not be a sensible idea for certain types of application. If we're talking about just general network flow at a typical core internet router, I still think this is accurate. If we're talking about very specific servers where the traffic is entirely mice, then this is a bad idea.
Are you talking about the router just before?
So every router in the path has to handle every packet.
Okay, but I'm saying the increase in number of packets will be 2.7%.
That's not right. At the first router, right outside, he's right. At the first router, immediately in front of your web server, the increase in number of packets will be 100% if you send every packet twice.
I'm not proposing that you send every packet twice. I'm proposing you send the very first packets in a flow multiple times. So if it's a web server which serves mice and elephants, then the increase in traffic load will be small. If you have a web server which serves only mice, then this is a bad idea.
The other thing you're describing there is a SYN flood.
Is what?
A SYN flood. You've just described a SYN flood. In other words, I send a whole bunch of SYNs to a machine from a source, and I expect the machine to send back ACK. You just open up all these sockets. That's why we have SYN cookies, to slow that down and to protect the server from getting flooded with half-open sessions.
Why does it need more?
If I send you a SYN, you're going to send me a SYN ACK.
Okay.
If I send you 5 of them, you're going to send me 5 SYN ACKs. You've opened up 5 sessions one after another.
I don't know enough about TCP internals. Don't the duplicate copies of the SYN go to the same half-open connection?
Duplicate copies of the SYN? You would send 5 different, you're going to see 5 different SYNs coming. I'm going to open up 5 different sessions, or I'm going to see 5 duplicate packets, which is a bad thing.
So you drop 4 of them and keep one.
This thing is they're still processing.
So if they send the exact
I have to still have to
sequence
receive
number,
the SYN in, and I've got to process every one and determine it's a duplicate, then have duplicate packet
To me, it looks like a duplicate packet if I'm host.
Yeah, but you don't have to respond to all five.
I've
Yeah,
got the
but
process
you've got an
all five.
interrupt for each of
I
them,
agree.
first of all.
You do.
I got a series of interrupts. I may respond to all five. I may close one session, start the next one, close one session, start the next one. It's all very specific to the device. It's still, in any case, the SYN is the
Well, I
most.
think he's implying that you shouldn't do that. You should like.
If you send 3 copies,
Mhm.
I'm gonna have 3 SYNs hit me. I'm gonna have to work on all
You
3.
process all 3 and you drop 2.
But to drop the 2, I still have to process all 3.
Yeah, so
It's still
it
processing,
definitely,
you take a hit.
this is really a serious hit on web servers where the quantity of serving mice is a big issue. I don't know enough about just sort of general network architecture to know how much that's a bottleneck in things which are happening. So I'm going to go on to talk about this point, about the network characteristics of these. Here are several different pictures of packet drops in the internet. This is for measuring end-to-end performance. Here's a measurement study from around 2000 of a link between a US university and Sweden, which decided average packet drops is around 3%. They also looked at the correlation between packet drops, and basically, if you send 2 packets more than 50 or 100 milliseconds apart, then they will be pretty much independent. So that's a plausible time. I think it's silly going less than 50 milliseconds, but 100 milliseconds should be safe. Here was another measurement study. This is looking at a wireless link where it alternates between periods of virtually 0% loss going up to 80% loss for when they turn on a milling machinery in the room next door. But this figure of 100 milliseconds, it was roughly true there as well. And then there's this theoretical work which says that you would expect to see bursts of drops in a router, and the bursts of drops ought to happen roughly separated by something of the order of several round-trip times. So these are several different pictures of correlations, and they all go to support this idea that in the network this 50 to 100 millisecond timescale is roughly the right idea.
Where does it come? Where does that magic number come from?
I only can give an answer for that based on the theory side. And the theory side says that it's about the control loop, the interaction between TCP and the queuing behavior, that TCP sending data, it causes bursts, it backs off, and it backs off too much, and then it goes up and causes bursts again. So that's basically what I'd expect TCP to do, to create correlations over this sort of timescale.
Double the round trip time or something.
Yeah, that sort of thing. I mean, the precise multiple of round trip time depends on the network.
I would assume that you have a series of flows all in sync together causing the problem to enable congestion.
Yes, and that's the linking back to the work on buffer sizing. It turns out that the buffer size is what causes synchronization. If you set your buffer wrong, then you'll induce synchronization between the TCP flows. The buffer at the bottleneck router, the buffer that TCPs are responding to.
Most of the time.
Yeah, I mean, most of ours don't care with TCP, they're just switching an IP. I mean, it makes sense at 50 to 100 millisecond time makes sense because of the housekeeping routines performed in a router to clear out congestion.
No, I'm not talking about what the queuing is there. I'm talking about the interaction of the control loop. So TCP sends stuff. The TCP is responding to congestion. Right. Congestion happens over the time scale of queuing phenomena there, and then the feedback comes, and then TCP reacts. And so depending on how big the buffer is in this bottleneck router, the buffer size will determine the dynamics of this round-trip time control loop, and that will induce the correlations and synchronizations depending on the scale of the buffer.
Let me suggest we hold questions now.
Yeah. Latencies. Well, you can't do anything much about the speed of light. I looked up what are acceptable latencies. Answer 220 milliseconds for playing Counter-Strike, 50 milliseconds for playing Wolfenstein, 5 seconds to download the Washington Post. All right, now on to theory. Problem statement. I want to know how well do network transactions perform over unreliable networks, and how should we design network transactions to make these things more robust. This is basically what people have done so far. Typically you assume a synchronous network, or you assume an asynchronous network with reliable delivery, and you ask the question, what's the execution time of the algorithm, the number of messages, and you look for limit theorems as n, the number of nodes in the system, tends to infinity. There's a very large and well-established study of distributed algorithms based on this sort of way of looking at things, which I don't think has anything useful to say for these particular types of problems. First thing, assume an asynchronous network. I'll cross that out. I mean, the internet's just unreliable, asynchronous. That's what we have to live with. It's no use proving a theorem which says that it is impossible to reliably deliver a web page. Next question, what's the execution time and the number of messages? Well, I don't like this thing, the number of messages, because it will be an impact on the server, yes. It won't be an impact on the network. The thing I have most trouble with is this one. They look for a limit as the number of nodes n tends to infinity. The trouble with that is that you just can't look at interesting networks if you say n tends to infinity. If you say, I'm going to look at a network with n nodes, then let n to infinity, you have to impose some very regular structure on the network to get answers out. So you can't have answers which say, well, it depends on this round-trip time and this round-trip time and the way they interact. So this n tends to infinity is just a bad way, I think, to proceed. I'm going to suggest a different way of doing these limits. I'm going to have a fixed n, fixed number of nodes in my network, fixed topology, fixed round-trip times between them, and I shall look for asymptotics in packet drop probability p, as p tends to 0, because it's a starting point. It will give me some answers. This is where I'd like to end up with, ideally. Something like, how does the performance of NFS degrade as the network becomes crummy? That would be a wonderful point to get to at the end. I'm definitely nowhere near that yet. So I'll give 3 examples of network transactions. First one's a very simple question. It's reliable delivery. I'm imagining a sequence of links, each link with its own packet drop probability and round-trip time. And let's suppose I want to send a message from here to here, and I want to make sure it's sent reliably. And I'll look at 2 different ways of doing it. First thing is hop-by-hop reliable delivery. I'd send a packet. As soon as this receives the packet, it will send an ACK. As soon as this receives the packet, it will send an ACK, and so on. And this node here will keep on sending until it gets an ACK back. So hop-by-hop reliable delivery. Or you could do end-to-end reliable delivery. Just treat these nodes as dumb things in the middle and wait for the message to come back. And so what's the performance metric? Well, what you could do, as I suggested before, is you cut the retransmit timer to be very short. And if you make the retransmit timer very short, you can achieve reliable delivery very quickly in either case. So it's not a good enough question to ask just how long does this take, because you can make it be arbitrarily quick by being arbitrarily aggressive. Instead, I'll ask a different question. Suppose we've tuned the retransmit timeouts to achieve reliable delivery within a certain time frame. How many retransmit timeouts does it need to use? So yes, this is saying that it's retransmit timeouts. It's computational power at these nodes which matters, which we need to control. And the answer basically is if some PI, if some packet drop probability on one of the links is particularly high, then hop-by-hop is better. Otherwise, end-to-end is better. Well, this won't be news to anyone. I mean, everyone knows you have hop-by-hop reliable delivery, at least for the wireless link from you to your wireless base station. And then there's end-to-end reliable delivery over the core of the internet. So the answer here is not at all surprising. It's just nice to be able to write down a simple model which gives you some algebraic way of getting to this answer. Here's another example. This is retrieving the web page. There's the Hotmail web page. So here I'll ask, what's the expected time until the web browser retrieves the entire page as a function of round trip time and packet drop probability? Actually, there are three different flavors, three different versions of HTTP, which all give different answers. In HTTP 1.0, for every single one of these items, you open up a new TCP connection. And the standard is to have no more than 4 simultaneous TCP connections. In HTTP 1.1, they decided that was a bit silly because it's stupid sending SYN for every single item when you're typically going to the same server. So HTTP 1.1 says, well, we'll pipeline them. I'll send the SYN-ACK once, but then thereafter I'll send multiple. I can send a request, get the answer back, send a next request, get the answer back, send the next on a single TCP flow. And the default is to use 2 TCP flows. And then there's HTTP 1.1 with pipelining, which is similar, but you're allowed to do the SYN-ACK request, 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 get the answers back simultaneously. These numbers, there's some interesting stuff behind the numbers here. There's no more than 4 TCP flows. Many people think it's to be kind to the network. If end users could open up a very large number of connections, then it would flood the network. That's actually not the reason for the number 4. Based on archaeological work through very early email lists to do with Netscape and Mosaic, they chose the number 4 because they imagined a dial-up user on a 56K modem who's got 5 simultaneous TCP connections open. If you imagine a typical round-trip time, each of those 5 TCP connections has a window size of roughly a bit under 1 packet, which messes up the ACK clock, and so the performance for the user is terrible when he gets that little bandwidth per flow. So they put in this number 4 to save the user from themselves. It was sensible if you have users on 56K modems downloading large items. It's completely useless nowadays when we have fast connections and we're downloading mice. I couldn't find any explanation of why they did this number 2. This pipelining thing, Firefox claims it's the only web browser which implements pipelining. When I last checked, the Internet Explorer blog said they were not implementing pipelining because the way proxies and so on are set up, if you try and implement it, it just won't work. So I reckon that Firefox implements it, but it just doesn't work and they don't realize.
There was actually some theoretical work done on this a while ago, and one of the problems with pipelining obviously is you can have weird head-of-the-line blocking problems. If the first request you send, the web page is generated by some database, the database is stuck. Now your second request might be for a stupid image, and now it's still stuck.
So I asked, the calculations are for the Google web page. I asked, how long does it take to retrieve the web page? Well, for HTTP 1.0, 50 round-trip times plus 30 times packet drop probability p times retransmit timeout plus O of p squared term. So this is what I mean by looking at asymptotics in terms of p. And you get this formula just by reasonably simple counting of what the possible outcomes are. HTTP 1.1 makes virtually no difference to this. In fact, if you have a lossy network, it makes things worse. And HTTP 1.1 with pipelining, assuming the pipelining is all done right and there aren't large delays at the server, then it's got much better performance. The trouble here is that the web pages are typically structured to be taller than they are wide, and the pipelining just doesn't help you very much. And it's the restriction to 2 TCP flows which was the killer. Here I looked at the different email service providers. I said that was the old version of Google that I looked at. In 2008, they updated their web page and it's faster now. This is what Hotmail Live is. It's still substantially longer than the 1 round-trip time we'd like in an ideal network. Okay, so those are two very trivial examples. If all I was going to talk about was the performance of web page download, there'd be no point me talking. You can do theory for that easily. I want to look at more interesting algorithms. Distributed algorithms are just fun. And so to talk about distributed algorithms, I need to be more clear about what the objectives are. This is what I call the hierarchy of needs for a distributed algorithm. And I'll work through the bottom three in the next few slides. Composability of analysis, safety, and liveness. All right, composability. Let's just take this example of reliable delivery. Reliable delivery happens at the MAC layer, like you to your Wi-Fi base station. There'll be reliable delivery of cells there. Reliable delivery happens in TCP end-to-end. It uses timeouts and gets reliable delivery of packets. And then there's reliable delivery implemented in JavaScript. So yeah?
I would say the MAC layer, it is the opposite way around. Often it's unreliable. In most cases, unreliable delivery. If you're running on Ethernet, it's absolutely unreliable.
Yes. So there's only some, but for wireless, they need to have reliable delivery at the MAC layer because otherwise it would just be too crummy.
After that, it's absolutely fully unreliable after that and everything.
Yeah. So there is some reliability implemented here, only in some networks. So what's puzzling here is that there's reliable delivery done at all different points in the network stack. How do these different mechanisms interact? If you really want to achieve a certain level of performance, how should you tune these things? Should they be communicating in any way? I don't know. It would be great to have a type of theory which lets you talk about questions like where in the network stack should this functionality be done. Safety. An algorithm is safe if, at all instants, for every possible execution trace, certain appropriate invariants are satisfied. I'll give an example. Here's an invariant. If Juliet is pretending to be dead, then Romeo knows the plan. So this is an example of a bad network transaction. Friar Lawrence sends a message to Romeo saying, Juliet will pretend to be dead. He sends a message to Juliet saying, pretend to be dead. And this message was dropped. This message got through, and it ended in tragedy because it doesn't satisfy this invariant. If, however, you had structured the transaction differently, it would have been perfect. It would have been a comedy rather than a tragedy. Okay, so basically we want algorithms to satisfy certain safety properties, and different types of tasks need different safety properties. I talked about probabilistic models with packet drop probability P and so on. From what I've seen, people want safety property to be satisfied for every possible execution trace. So this is a bit odd to a probabilist who's used to thinking of almost surely. Basically, computer scientists don't trust probabilists enough to write good probability models, and so you want to make absolutely certain that nothing can go wrong. You're only interested in algorithms which won't mess up. The liveness. A lot of the work on distributed algorithms has looked at algorithms which look something like this. Let's say I'm trying to write a program which has a leader election component. For example, I'm trying to elect a name server in an ad hoc wireless network. You might write let x equal get leader, then you'll send a message to the leader. And the get leader function might look like this. Well, true, it continues to exchange messages, and as time runs longer and longer, it'll be more likely to have a correct answer. But many of these algorithms which people have analyzed, they never actually terminate, and that's not terribly useful. I'll be interested in algorithms in which each node eventually finishes its execution almost surely. So, hierarchy of needs. We want our analysis to be able to tell us something about layering and composing. We want to look at algorithms which satisfy suitable safety properties. We want algorithms which should terminate almost surely. I've written this almost surely because there's always a possibility that the algorithm will never terminate. For example, if I'm retrieving a web page, it's possible that every single message between me and the web server would be dropped, but it's so unlikely that we won't worry about it. So probabilistically, I'll say almost surely the algorithm should terminate. Correctness, with high probability, when it terminates, it should give us the correct answer. And latency, I'll be interested in the expected time to terminate. So a hierarchy of needs, 4 different levels of probabilistic guarantees. And here's a complicated and interesting example of an algorithm which I'll work through in this way. This is the leader election problem. Leader election is an ancient problem, but a good place to start. I looked through a bunch of different leader election algorithms. I couldn't find any which were simple enough for me to analyze in this, trying to understand the performance characteristics on an unreliable network. So I had to come up with my own very simple leader election algorithm. This is what it does. I'm imagining you have a bunch of computers on a network, a shared network with a hub, a collection of princes and courtiers, and the objective of the algorithm is to elect one of them to be a leader. And a suitable safety property, it seemed to me, is that if X thinks Y is the leader, then Y thinks that Y is the leader. I'm thinking, for example, of trying to elect a name server in an ad hoc wireless network. I read that Windows XP does this. When you set up a wireless ad hoc network, it elects one of them to be the name server. I found that whenever I set them up, it never did that reliably, so I wanted to look at this. So this means that, for example, if I think that you're leader, and I send you a message assuming you're leader, then at least you'll not choke on the message. That's a plausible safety requirement. It's no good requesting that we only ever elect one side of the leader. For example, this side of the room might elect a leader and that side might elect a leader. And if all messages between the two sides of the room are dropped, then there's no way to insist that we only ever have one leader. So it's no good. And the termination property, once we've accepted a leader, we should not change our minds. And this algorithm, I guess I won't go through the details because this is it's an algorithm based on 2 rounds, and it has a bunch of messages here, but that's not. I won't dwell on it. What's good is that I was actually able to get somewhere with analysing it. Lemma, the expected number of leaders elected is 1 plus 2p plus O of p squared. In other words, if p is 0, you'll have 1 leader elected, which is a very useful property. If p is small, there's a chance that we'll have 2 leaders elected. And also, you can work out the time it takes for this algorithm to finish explicitly in terms of the message delays in this network. The completion time, it depends on who the closest nodes are to the hub. So it's nice to have bounds which explicitly incorporate what the structure of the network is. And it's nice that it depends on who's closest. It doesn't slow down if there's someone who's 3 miles away. All right, so this really is just a proof of concept. A simple classic problem, fairly simple algorithm, and that's a starting point for this project of analysing distributed algorithms in unreliable networks. Okay, so this is what I've talked about. A definition: the network transaction is a coordinated exchange of short messages between computers on an unreliable network. I'm interested in algorithms which satisfy safety, liveness, correctness, and have good latency. I want to know how well do these algorithms work when the network is unreliable, and I want answers which tell me about how the performance relates to the structure of the network. And the real challenge is trying to do it in a way which lets me say, for example, I'm using hop-by-hop delivery here as a leader election algorithm, which is then part of something bigger. That's a very big challenge, I think. Here are some very, very simple suggestions. We might tweak TCP to send mice more aggressively, although not too aggressively. Maybe we should allow web browsers to send several mice simultaneously. This limit of 2 isn't really suitable. Here's something which should be interesting from the theory point of view. Devise some sort of standard template library of distributed algorithms where in the standard template library you say what the running time and memory requirements are as a function of problem size. I'd like to have a library of algorithms where you say what the running time and correctness is as a function of network reliability. Well, here's a way out idea. This idea of layering, the idea that reliable delivery is implemented at many parts of the network stack. You could imagine when the top level function is called, like when the user clicks on something, it creates a timeout pool. And every single timeout lower down in the network stack, in the API stack, it subtracts from this timeout pool, and when the timeout pool runs out, it returns control to the user. That way, the programmer would have some control over the user experience. There's no point trying to do this unless you have some sense of how long different network tasks should take to complete, and so that's why it's nice to have some way of analyzing the performance of network tasks. Okay, so it's just restating the summary. Thank you.
Are there any suggestions? So when I look at the second to the last slide, right? The first thing that occurs to me is it'll be great to have an analysis of how the first two suggestions affect the network itself, both in the core and at the edge, right? So these are great suggestions, but we really just don't know. And the part of the discussion and questions that came out are really about that, like how does it affect the network? And the second thing is, and I want to know if you've thought about that, if you have any thoughts on that. The second thing is, what does the web server do? I mean, some of this stuff is not controlled by people in this room. It's tough. Tweaking TCP is a really, really hard thing to do in 2008. Web browser design is fine. We have IE here, but it's a tough thing to do as well. On the stuff you can control, usually is the web server. Is there anything you can do there?
There are actually suggestions about this out already. So one of the things, for example, this is not something we can easily do with the web server, but it's a fairly easy to do TCP. The Win2 gateway, which is our standard default server that serves all our properties, has the initial congestion window of 2 packets. The RFC recommends 1793. I think that it can get as large as 4. It would cut at least 1 round trip time, just like that, from our transfers.
Yeah, that's great if you have enough packets to fill up that initial congestion window.
That would be for most web pages. So most web pages are more than about 4,000 bytes.
The pages as a whole are, but for example, on these things, many of the items are just half a packet big.
Sure.
So, yeah.
For pages that are under
so that's definitely a great idea, and I think that adding a little bit more aggressivity, like sending the thing, let's say, send a packet and then 100 milliseconds later send the packet again.
Well, if the customer, the receiving system can't handle it, if he has an AccuBack or whatever, what's the purpose of sending it? If you're going to drop it at the receiving end?
Why can't he handle it? It'll just be a duplicate packet if he gets them both.
Again, you create duplicates.
Yeah. So there's definitely a question about how much of a load that would cause.
Because you're not causing IOs at the receiving end and the sending end too.
Yeah, but those things are cheap. Processing power is cheap, right?
Not if the receiving system is on demand. I mean, a lot of our customers do not have the latest and greatest PC. Also, you're hitting firewalls, proxies, other things that have to look at these extra frames.
So I agree with you. I think part of what he's saying is, in 2008, some of those things are less a problem than they were before.
For the host.
Yeah.
Not, I'm talking about everything else. It still becomes an issue of you now sending dupes again, which somebody try and stop.
Time is on his side, though. I mean, hosts will get faster, networks will get faster, mice will get more numerous.
Yeah.
And to do this fully, you definitely would want to think about redesigning the hardware, maybe going that far to design hardware which is more used to receiving duplicate packets. That one's harder to do. This tweaking TCP to send mice more aggressively, I think that's very easy to modify because this modification doesn't require any. You can do it in one place. Like you could do it just to the end system, and it doesn't require any cooperation from the network.
Wait, this is not like a tweak on Vista, right? You have to literally release another version of
You have to release a new TCP IP.sys.
stack.
Absolutely.
Yeah. So like that would happen fairly quickly with Linux, I suppose.
Load balancers,
Yes.
you have to modify.
You have a whole bunch of things.
Firewall.
Wait, these things should all cope with duplicate packets because
Are you sending exactly the same IP ID? I mean, is it exactly?
it should be precisely the same packet.
When you're sending duplicate frames, you're going to have errors everywhere. You're going to have error alarms everywhere.
You will have, so the stack would have to be modified fairly carefully because first of all, the stack has to be informed by the application that, hey, this is a mice flow. Okay, and that to some extent you can deduce that because maybe the connection already closed. So Windows actually has something already, where the flows are very short, less than 8K, it does something different. But then now you have to inform it specifically that, hey, this flow is only 2 packets long or something along those lines. Now do something special.
Well, that's why I suggested send 3 copies of the first packet, 2 of the second packet.
Unless
It doesn't. I said for every single flow, send 3 copies of the first, 2 of the second. That would be a simple way to be more aggressive. Now, should the rest of the network cope with duplicate packets?
You're now going to introduce, as a standard function, an error condition that we look for. Because a duplicate packet that's exactly the same as any other packet indicates a loop exists in the network. Therefore, I need to go hunt it down and kill it quick.
Why does this indicate a loop? I thought that's not part of the...
If I have a packet in the network, it's been generated. And then a system looking at that, passing it through, sees exactly the same packet again. Okay, by the way the networks are set up, which have a single path in the network, if I see the same packet twice, then I must have a loop in the network. If I have a loop in the network, then I need to go kill it quick, find out where the error is. So duplicate packets are always an error in the network at every layer.
That was not my understanding of the original IP stuff.
If I see a packet once, and I see it again, exactly the same, if you're sending me a retransmission, you have differences in the packet. The IP ID is different, there's other things different, timestamps are different, the CRC is different, whatever. If I see exactly the same packet twice in the network, the only reason I see that packet is because a loop has existed. Think about it. The only way you can have it is a loop right now.
Do internet hosts, do they react to duplicate packets in any particular way to IP stacks?
If the duplicate packets are exactly identical, that's some of the attack monitoring tools consider that as a man-in-the-middle packet replay type of attack.
Yep.
So it might trigger some of those.
It helps if he can make the packet look a little different.
So you can make it have a different IP ID, for example, and that might help. Then you have to make sure that this end system does not send out a do back, because if it sends out a do back by mistake, this host will reduce its condition window size, and you would have shot yourself in the foot.
If you make the packet different, then the receiving system may set up a new session. Now you have 2 sessions open because now it's not a duplicate packet.
Well, I guess we're going to have to change the host. I'm not so sure about the switch, but the switch is going to work harder because you see more interrupts, but there'll have to be host changes.
Yes.
This is something that you really want to be careful of because you're going to kick alarms off all over the place.
It's like the ECN bit, which if you set ECN capable in packets, then it causes Comcast cable modems to simply shut down completely. It's one of these things which should never have happened, but unfortunately it does.
And they say we're going to reject it.
They don't just reject it, they crash.
Yeah.
No, you're not supposed to crash on things you don't understand.
No, I understand
that. That's a bug.
Yeah, it's a bug, but we ignore it. We ignore it in the network now because everybody wants to be the highest priority.
But let's go back to, let's not worry about the network for a second. Let's think about the end systems. You just have to change the HTTP access and then the clock to be more aggressive. At that point,
Jay has a good suggestion. If the biggest problem is that our first timer is 3 seconds, why don't we change that? That requires the least amount of change. And we don't inject any extra packets. And, we know that most round trip times in the world now rarely exceed 250 milliseconds. Let's say the first timer to be something on those orders. Why bother with these duplicate packets?
And that's a change you can make without releasing the stack, right?
No, that's a change you will have to make by releasing the stack.
Oh, you have
Unfortunately, yes. I don't think that's a registry setting. That's not a registry setting.
Okay.
It is, it's not exposed.
I had to look at the pipelining options in Firefox. In Firefox, you can tell it how many simultaneous connections to open various configurations. The default is 2 simultaneous connections, and it allows so many things to be pipelined on each of them. And I set the defaults. I changed them from being 2 or 4 to around 5,000, and it had no measurable benefit. I guess there were either bad implementations or head-of-line blocking or something similar. I think also that more intelligent web browsers, more intelligent ways to cope with mice would be well worth doing. I read about a group which it's basically a group of Ajax developers with a wish list for what they want next generation of web browsers to do. This was the first item on the list, I think. They allow us more than 2 simultaneous connections.
I mean, it's kind of depressing that HTTP 1.0 is a little better, but or in practice on 1.1.
Maybe it was a design goal that they didn't want 1.1 to be too much more aggressive. I don't know.
Your third point there, well understood latency. What do you mean by well understood latency?
I mean things like like in the standard template library, you say running time is O of n squared. I'd like to say something here like running time is such and such a function of latency and packet drop probability.
So again, Damon will be around. A few more hours today, or what's your plans?
A few more hours today.
Okay. And if there's folks that want to talk with him further, he's around next week, starting Tuesday. Just let me know. Albert at Research. No, Albert at Microsoft.com. Sorry.
Thank you.
Thank you.
Albert, a lot of stuff.